In this video, we're going to look at the chi-square test for independence. So definition. The chi-square test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. The null hypothesis is that the variables are not associated, or in other words, they are independent. The alternative hypothesis is that the variables are associated, or in other words, they are dependent. So we're going to be looking at a contingency table, and again, what we're going to be looking at is, are the row variable and the column variable independent or dependent? Are they associated or are they not associated? And so again, our null hypothesis is going to be that they're independent, meaning they're not associated, and our alternative hypothesis will be that they are dependent or they are associated. So we're going to assume that they're independent, in other words, that they're not associated unless our evidence indicates otherwise. So the structure of this test is going to work a lot like the goodness of fit test worked previously. We're going to compare what was observed to what is expected. And so we need to be able to determine what the expected frequency is for each cell of a contingency table. And so that's what this screen is about. Expected frequencies in a chi-square test for independence. To find the expected frequencies in a cell when performing a chi-square independence test, multiply the cell's row total by its column total and divide this result by the table total. That is, the expected frequency is equal to the row total times the column total divided by the table total. Now this is a shortcut that is derived in order to be able to figure out the expected frequency of a contingency table cell. So this will make a lot more sense when we look at an example. So we're going to have an example here, and we're going to use this example and do a complete test for independence, but we're going to start by finding the expected values. So prenatal care. An obstetrician wants to learn whether the amount of prenatal care and the wantedness of a pregnancy are associated. He randomly selects 939 women who had recently given birth and asks them to disclose whether their pregnancy was intended, unintended, or mistimed. In addition, they were to disclose when they started receiving prenatal care, if ever. The results of the survey are as follows. So if we look at this contingency table, we can see in the rows we have the wantedness of the pregnancy. So was the pregnancy intended, unintended, or mistimed? And then we have in the columns the months pregnant before prenatal care began. So we have less than 3 months, we have 3 to 5 months, we have more than 5 months, or never. So of the 939 women, 593 of them intended to get pregnant and they received prenatal care in less than 3 months. 26 were intended and received prenatal care from 3 to 5 months, and 33 were intended and received prenatal care more than 5 months or never. And so on. 64 unintended received prenatal care less than 3 months, 8 were unintended 3 to 5 months, 11 were unintended more than 5 months, 169 were mistimed and less than 3 months, 19 mistimed in 3 to 5 months, 16 were mistimed in more than 5 months. So we want to compute the expected values in each cell under the assumption of independence. So assuming that the row variable and the column variable are independent of each other, not associated, then we want to compute the expected values. And that is what we saw with this formula. Assuming that we have independence, we're going to calculate the expected frequencies by taking the row total times the column total divided by the table total. So the first thing we're going to have to do is figure out the totals. So if we add up 593, 26, and 33, just add those together, that is a total of 652. So a total of 652 intended to get pregnant. If we add up 64, 8, and 11, that is 83. 83 did not intend to get pregnant. If we add up 169, 19, and 16, that is 204. And so 204 of these pregnancies were mistimed. And if we add that together, that is a total of 939. So this is the first row's total, the second row's total, the third row's total. This is the table total. In the same way, if I add up this column, 593 plus 64 plus 169, that is 826. So 826 received prenatal care in less than 3 months. If we add up 26, 8, and 19, that is 53. So 53 received prenatal care at 3 to 5 months. If we add up 33, 11, and 16, that is 60. And so 60 of the women received prenatal care more than 5 months or never. And again, if we add up 8, 26, 53, and 60, that adds up to 939 for the table total. So here we have the column totals. So if I want to calculate the expected values for this table, I'm going to take the row total times the column total divided by the table total for each cell. So for this cell here, we observed 593 women in this cell in our data. So what would be expected if these two variables are independent? Well, for this cell, I'm going to take the row total, which is 652, times the column total, which is 826, and divide by the table total, 939. So if I bring in my calculator, I'm, for this cell here, going to take the row total, 652, times the column total, 826, and divide by the table total, 939. And that is equal to 573.538 if I round to 3 places. So I'm going to write that here, 573.538, and I'm going to put that in parentheses to indicate that this is the expected value. I'm going to do the same thing for this cell. So for this cell, it's in the first row, second column, so I'm going to take the row total, 652, times the column total, 53, divided by the table total, 939. So that is going to be 36.801. So that is our expected value for that cell. For this cell, it is the first row, third column. So I'm going to take the first row total, 652, times the third column total, 60, divided by the table total, 939, and that is 41.661. So here we get 41.661. So next, we're going to do the row total, 83, times the column total, 826, divided by the table total, 939. And so this expected value is 73.012. Likewise, I'm going to take the row total, 83, times the column total, 53, divided by 939, the table total, and that is 4.685. So this is 4.685. Same, 83 times 60 divided by 939. So this expected value is 5.304. For this cell, row total is 204 times column total 826 divided by 939, the table total. So that is 179.450. Likewise, row totals 204 times column total 53 divided by table total 939. So this is 11.514. And last but not least, 204 times 60 divided by 939, and that result is 13.035. So 13.035 is our expected value in that cell. So we have the observed and we have the expected. Now what's going to happen when we do our test, we're going to use the same calculation method. We're going to compare the observed to the expected. So you can see there are differences between what was observed and what's expected, but the question is that statistically significant? Is that significant enough to say these are not independent, or are these independent? And so that's the way our test is going to work. We'll look at one more sheet, and then we'll move to a new video. So the test statistic for the test of independence. Let O sub I represent the observed number of counts in the ith cell, and E sub I represent the expected number of counts in the ith cell of our contingency table. Then chi-square equals the sum of O sub I minus E sub I squared divided by E sub I. Notice again, this is the exact same calculation that we used in the goodness of fit test. The only difference is that here we're looking at a contingency table, so we have observed and expected values within the contingency table cells. Anyway, this approximately follows the chi-square distribution with R minus 1 times C minus 1 degrees of freedom, where R is the number of rows and C is the number of columns in the contingency table. So again, the way we're going to calculate our degrees of freedom is different in this case. So the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. Now again, it follows this chi-square distribution, provided that 1, all expected frequencies are greater than or equal to 1, and 2, no more than 20% of the expected frequencies are less than 5. So we have these same conditions that we had for the goodness of fit test. Pretty much everything is the same as the goodness of fit test, except the way we calculate the degrees of freedom when we have this test for independence. So rows minus 1 times columns minus 1 instead of k minus 1. But the way we calculate chi-square is going to be the exact same, and it's going to follow a chi-square distribution. So that concludes this video. In the next video, we're going to actually conduct a chi-square test for independence.